Swayam Prabha. Digital India. Educated India.
Welcome. We are continuing our discussion on fundamentals of parallel computing, the first module of the course High Performance Computing for Scientists and Engineers, and we are in the last lecture of this module, which is our lecture 11. We are continuing the previous discussion which we have started on performance matrix of parallel systems. As I was discussing that a parallel system is deployed to do high performance computing simulations. Why do we need high performance computing? Because simply if we solve using a simple computer, which we have been mentioning as sequential computing, it might require enormous amount of time if you are trying to solve a very large problem. In order to reduce the time, in order to get faster solution, we try to do high performance computing, which is typically using multiple computing systems, using multiple CPUs in different architectures to solve a single problem, and these CPUs work in parallel while they are basically trying to solve different parts of the same problem, but they are working parallel. And we have seen that when all these CPUs are working in parallel, they will have some overheads due to interaction between them, due to setup of the parallel environment, due to some other issues like improper load balancing, latency of certain systems, etc. Therefore, it is extremely important that we find out a quantitative metric to see how good is the parallel environment or the parallel system architecture, as well as how efficient is our algorithm by which we are trying to solve a problem, not using a sequential computer but using multiple computers. How we can understand that it also depends on how we are designing the algorithm. We have discussed about design of parallel algorithms and how we are utilizing different systems in the parallel infrastructure. So we have introduced about some concepts on performance of parallel systems in our last discussion, and I am continuing with this. So we have introduced performance metrics which include the parallel computation time, the speed up, the efficiency, the cost of computation, etc. And we have also discussed about overheads and efficiency, and we have seen that if we consider a parallel system to be very efficient, that means that if we are increasing the number of processors, the speed up is increasing almost linearly. The benefit is almost linear. If we are adding 2 more processors, or if we are doubling the number of processors, the computational time is getting halved. That is a function with efficiency, a parallel system with efficiency 1, but there is a we really cannot achieve that efficiency because there are overheads. As we are increasing number of processors, they are interacting in between them. There are some other issues like load balancing, there are some other issues like strong sequentiality in some parts of the algorithm, which does not make it fully efficient algorithm, and we lose some efficiency, we see a reduction in speed up. So we will discuss about this efficiency and overheads little more. We have already started the discussion in our last class on parallel on the performance matrix of parallel systems, and then we will see something called an isoefficiency function, which is a very important parameter in order to estimate that what should be the optimum number of processors in which I should run my parallel program to get best efficiency as well as to get the right speed up. One thing we should also not forget when we are discussing about parallel systems, that if we are having a large problem to solve and this is running over a large number of computers and processors, these computers do not come for free. We have to spend substantial amount of money in establishing the setup, as well as for running the setup. There is huge operational cost, including the energy investment. Also, these computers are they as they require energy, they do contribute to our energy scenario as well as to global warming. In data centers or the hubs in which we host the parallel computers, they are infamous for sources of global warming. They have very high carbon footprint. So, we should be very judicious while deciding that what is the optimum number of processor and what is the optimum size of the computing environment in computing infrastructure that we should use to solve this problem. We should not take it for granted that we can increase the number of processors as much as possible and we will get better efficiency, or we will get the job done in a more faster way. We also should be judicious in deciding how many processors we should work with, and if somebody is in some place where there are a lot of computational resource, he must be happy, but in general everybody working in high performance computing are challenged with the problem that the computational resources are limited. You do not get large number of processors. If you are submitting job to a very high end supercomputer, you see that you have to your job will go in queue and you have to wait few days till you get, say, for 5 days runtime and get some part of your problem solved. You may not solve the entire problem in one set of run. So, availability of the computational resource is also one very serious issue, and therefore, understanding the performance metrics and understanding how to decide what should be the optimum number of processors to get right performance, and also understanding the fact that whether the program or the algorithm we have developed is the right one or whether we need to do something else to get better performance out of it, these are very important. So, we will look about efficiency in little more detail. We understand that efficiency is an important parameter while estimating performance of the parallel systems, and in case a parallel system is completely scalable, that means if we increase the number of processor by twice, the time required will be halved. It will require half than the previous time requirement. We call that the system has the efficiency is equal to 1, but we understand that efficiency cannot be 1 because there are overheads, and as we are increasing number of processors, there are more interaction between the processors. In case of distributed memory system, in case of shared memory system, there are more race conditions, there are more false sharing, and cache coherency protocols are much required, and therefore there will be certain overhead. Also there will be some overhead due to improper load balancing, and efficiency will fall down. So, if we are increasing number of processors, we will not see that the speed is increasing by the same factor. We can see efficiency is a function of both problem size as well as number of processors, and we will see how. That means, if we have a large problem, whatever is the efficiency, if we increase the problem to a larger extent, efficiency will probably increase if we keep the number of processor fixed, and if we increase the number of processor for one particular problem, we will see the efficiency will fall down, and let us see it in detail. So, efficiency we have seen can be expressed as speed up divided by number of processors. What is speed up? Speed up is the ratio of the computational time required by sequential processor or sequential program divided by the computational time required by the parallel program, and this is also inverse of the ratio of speed of these two programs. Ratio that means speed up is ratio of the speed of parallel program divided by the and the ratio of the speed of the parallel program and speed of the sequential program. So, nevertheless, we get speed up is equal to sequential computing time Ts divided by parallel computing time Tp, and efficiency is S by P, which is Ts by Ptp. Now, if you understand what is Ptp, Ptp is the cost of parallel computation, and therefore, Ptp is the difference between Ptp is the sum of the sequential computing time and the computational overhead. So, we write it that Ts is equal to T0 plus Ts. PTP is equal to T0 plus Ts, which is overhead plus the sequential computing time. And dividing both sides by sequential computing time, we get efficiency is equal to 1 by T0 plus Ts. Turn this off. This T0 by Ts is the ratio of overhead divided by sequential computing time. Therefore, we can see efficiency is a ratio, is a function of the ratio of overhead and sequential computing time. What is overhead? Overhead, why does overhead occur? Overhead occurs mainly due to interaction between the processors or data transfer and load balancing. So, as we increase number of processors, overhead will increase, because more processors are there, more data transfer time will be required, and more processors are there. So, load balancing effort and latency due to improper load balancing will increase. So, this becomes a function of the number of processors, and Ts is the computing time for a sequential program, and Ts is simply determined by how large is our problem. So, you can see efficiency is a ratio of, is a function of overhead and efficiency is a function of the ratio of overhead and sequential computing time, or is a function of the problem size and number of processors. And we can say that efficiency is a function of ratio of overhead and sequential computing time, and therefore, it is a ratio of, it is a function of problem size and number of processors. We can understand from here that overhead is related with the number of processors. As we are increasing number of processors, overhead will increase. Sequential time is related with the size of the problem. As the problem is larger, the time to compute the solution in a single processor is also more. So, speed up is number of processors into efficiency. Simply we can write Ts by Tp, and which is P into 1 by T0 plus Ts, or 1 by P plus T0 by Pts. And now we can see that in case the overhead is very small, say in case T0 is a small number, in case it goes to 0, speed up becomes 1 by 1 divided by 1 by P, or speed up is equal to P. In that case, speed up is equal to P. That means, we are increasing the number of processors and we are getting the ratio of the computing time for that parallel program and the sequential computing time which is equal to the number of processors. So, if we are using the number of if we are using 5 processors, the computing time is 1/5 of the sequential time, and which is an ideal system, which is an efficiency one system. But it never happens because S is never equal to P, because T0 is never is equal to 0. So, there is a significant amount of overhead and it leads to reduction in speed up. So, we consider an example to look these things into detail. We consider addition of n numbers by P processors, and n is divisible by P. So, each processor adds n by P numbers and then communicate it over communicate its sum over this P processor network, and after this communication one processor picks up these values and it adds the additions which are local additions which are coming from all different processors. So, computing time will be in a parallel computing setup will be computing time for n by P numbers. So, what is adding n by P numbers? The computing time will be of the order of n by P floating point operations will be there, and communication time over P processors, because each processor has its local sum which is communicated and P processors are doing these things. And this communication time, sending data by a processor and receiving by another processor over a P processor network, it can be shown that this is of the order of 2 log P. Therefore, the total time requirement becomes of the order of n by P plus 2 log P in case of parallel computing of summation of n numbers in a P processor network. Now, if we try to do it in a single processor sequential system, there are n numbers, they will be added, there will be n floating point operation, therefore computing time will be of the order of n. So what will happen to the efficiency, that is S by P or Ts by Ptp, and we can see efficiency is 1 by 2p log p divided by n. And speed up will be efficiency multiplied by p, which is 1 by p plus 2 log p by n, or p divided by 1 plus 2p log p by n. This is, we have not considered load balancing overhead, we are only considering the communication overhead, because this is a completely load balance problem. So this 2p log p term, right, this is the overhead term here. In case this overhead becomes 0, speed up is equal to p, a perfectly scaled up system, efficiency is equal to 1. When this overhead can be 0? This overhead can be 0 if p is equal to 0, it can tend to 0, but there is no meaning of that problem. But the overhead can be 0, p is equal to 0, again undefined, p is very small, the overhead can be small. But the overhead also can be small in case n is large. So if we are, or sorry, if p is equal to 1, overhead will be 0, I am sorry, log 1 is 0, but that is a sequential program, it does not have any overhead. But if n is large, if we are solving for large number of numbers to be added, the problem size is itself large, then this number will be a small number and s will tend to p. So if we are solving in single processor, overhead is 0, but there is no point in discussing single processor parallel system. If we are solving for a large problem in small number of processors, then this will be 0, the overhead will tend to 0, will be small. So we have taken here from Grammar's book how overhead varies with number of processors, and we can see that as for one particular problem, as we increase p log p increases rapidly and overhead becomes overhead is large, therefore speed up becomes almost constant. Even if we are increasing more number of processors, you can see here, even if we are increasing more number of processors for a small problem, we are not seeing any change in speed up. For a larger problem, there is some change in speed up. However, speed up does not increase much if we are increasing the number of processors. Initially it increases, but then it becomes almost flat. But if we keep on increasing the problem size, keeping the same number of processors, say for processor number 16, if we keep on increasing the problem size, we can see the speed up is increasing. Why? Because as n is increasing, overhead is reducing, or the effect, or the effect of overhead in term efficiency is increasing. The effect of overhead in scalability or speed up of the system or calculation of efficiency of the system is reducing as the problem size is increasing. Overhead is p log p, which is fixed, which is only increasing with number of processors, but as the problem size is increasing, its effect in calculating efficiency and speed up is reducing because n is increasing. So with increase in n, we get better speed up. So we can, and the same thing happens for efficiency, therefore we can say that speed up is near linear as the problem size increases. If we take a much larger problem, if we take n is equal to say 10,000 or even more than that, n is close to a million, then we will see that this curve has become much flatter. So speed up becomes more linear as follows 45 degrees curve as the problem size increases. Efficiency increases if problem size increases. We can find also here as speed up increases, efficiency will become, as speed up increases, efficiency will approach the highest efficiency point, which is 1. But efficiency reduces if number of processor increases. Speed up becomes flat, the slope of speed up reduces, efficiency is speed up divided by p. Therefore, as number of processors increases, speed up becomes flatter and s by p will be a smaller number. So efficiency reduces as number of processor increases. So we can summarize this, that efficiency is a function of problem size and number of processor. As the problem size increases, efficiency is more. As the number of processors increases, efficiency is small. We will look into little more detail, that for a given problem size, if we increase the number of processing elements, the overall efficiency of the parallel system goes down. Given a problem, as we keep on increasing the number of processors, we can get better speed up, but the speed up curve will be flattened. The speed up will not increase as much as the number of processors are being increased. And this observation holds for all parallel system. Even if speed up is increasing, the rate of increase of speed up, or speed up divided by number of processors, S by P, that is not increasing, that is falling down. Therefore, efficiency is reducing as we are increasing number of processors for a given problem size. And single processor problem is the best efficient problem, it always have efficiency is equal to 1. But as we again, if we go to 2 processors, the computational time is less, speed up is more than 1. However, speed up by number of processors or efficiency is reducing, because speed up is not exactly following 45-degree line. Had speed up followed 45-degree line, efficiency would have been constant or 1, but it is not following a 45-degree line, again due to the fact that there are overheads, and the overheads are increasing as we are increasing number of processors. The next observation is, so we can see that speed up, though it increases, it becomes flattened down, and there can be cases where speed up is reducing. Actually, you have seen in the last problem, for a very small problem size, if you are using large number of processors, speed up is reducing. You can look into the last slide. And efficiency is also reducing, and efficiency is reducing almost asymptotically. So we can see that as number of processors are increasing, these terms 2 log p here and 2p log p here, these terms increase, keeping number of processors, keeping the problem size fixed, these terms increase, and therefore efficiency falls down. Speed up does not fall down, not necessarily it will fall down, but it slows down. In many cases, efficiency increases if the problem size increases while keeping the number of processors fixed. If the number of processor is fixed, but we are increasing the problem size, efficiency is probably increasing. And why is it increasing? Because the ratio of the overhead divided by the number of processor, which comes in the efficiency calculation, that is reducing. As we are increasing the ratio of the overhead divided by the problem size, that is reducing. As we are increasing the problem size, this ratio is coming down, and therefore efficiency is increasing. So efficiency in general, there can be cases where converse is true, but for the first thing, it is first part, that if you increase number of processors, efficiency will reduce, this is universally true. But if you increase number of if you increase the problem size, in general, or for most of the cases, the efficiency will increase. There can be some contrary examples, different examples, but in most of the cases it holds, that if you increase the problem size keeping the number of processor fixed, efficiency increases. So we can understand that for a larger problem with the same number of processors, efficiency will be more. For the same problem with increased number of processors, efficiency will be less. Now, if we have to solve a larger problem, should we increase more processors or not in order to get same efficiency? And that becomes a very important question here. And that, to address that question, we also need to know about isoefficiency function. Speed up or efficiency is a function of both number of processors and problem size. So if we have a larger problem, should we use more number of processors? That is the question. As the problem size increases, efficiency is increased. As the number of processor increases, efficiency is reduced. So how beneficial is to increase the number of processors to solve a larger problem? If we have a larger problem, if we are using same number of processors, we are getting better efficiency. In case we want to have same efficiency, better efficiency means speed up is the speed up increases. If we have to use same S by P ratio will increase more number of processors and will get better speed up, similarly better speed up in the similar ratio. Should we use more number of processors if we have more number of if we have a larger problem? For the same problem, if we use more number of processors, efficiency will fall down, speed up will be flattened. If we have a larger because we are always using high performance computing architecture to solve large problems. If from one problem we go to a larger problem, will it be judicious decision to increase more number of processors? That becomes the question. And what is our optimal function here? That we want to keep the efficiency fixed. We do not want to reduce in terms of efficiency, because we discussed about costs, overheads, etc. We see that it is important to maintain the efficiency of the computation. Can we get better speed up while increasing the number of processors for a heavier problem, or near constant efficiency? Can we get that? And what is the parameter by which we can decide this? So, you know, efficiency is 1 by 1 plus T0 by Ts, where T0 is the overhead time and Ts is the T0 is the overhead and Ts is the sequential time, that if we solve it in single processor, Ts will be the time. So, it will be important to see how overhead T0 changes while increasing the number of processors and the problem size. Well, overhead is so efficiency depends on overhead, because problem problem size and how overhead changes. If we can quantify the change of overhead, we can understand how efficiency is changing. Overhead is a function of both problem size and number of processors. Let us assume a sequential job which is running in a single processor, of course, and the single processor computing time is W. That is being executed in parallel. Now, this job will be executed in parallel by P processors, and the overhead is a function of the main problem size W and the number of processors. So, overhead is T0 W by P. So, efficiency is equal to S by P or W by PTP, which is equal to W by PTP is the cost, which is sequential computing time plus overhead. So, efficiency is 1 by 1 plus T0 W by P divided by W, if we divide both sides by W. Therefore, the sequential computing time W can be written as E by 1 minus E by simple manipulation T0 W by P. So, overhead can actually be expressed as a combination of implicit function with efficiency and the main problem size, sequential problem size. Well, if we have to maintain a constant efficiency, this E by 1 minus E term, if E is constant, this becomes constant. Therefore, W is equal to constant into T0 W by P. T0 is the overhead, which is a function of W or the main computing time of the sequential job, and P or number of processors. W is the sequential computing time, which is constant, K is also constant. Therefore, for a system where E by 1 minus E is constant, T0 W by P must be a constant. And what is T0 W by P? What is the function which relates overhead with efficiency with number of processors and the problem size? This function is known as iso-efficiency function. In this case, if we can keep K is equal to constant, efficiency is equal to constant by increasing number of processors, in this case T0 W by P is called as an iso-efficiency function. It determines how the problem size should increase with increase in processors, so that efficiency or K remains constant. In case I am changing P, how W will change, so that this function K will remain constant. And it is also seen that for constant efficiency systems or scalable systems, it has near constant efficiency systems, this value is small or overhead is small. So, if we have small overhead, it is following near 45-degree slope in terms of speed up, and efficiency is nearly constant. And this function, which relates overhead with the problem size and the number of processors, is known as iso-efficiency value. Well, so we can do a numerical experiment, or we can do some analysis on the algorithm and find out how overhead is related with number of processors and the size of the problem, and find out the isoefficiency function in certain cases, and that can help us to determine what should be the optimum number of processors for a problem. If you are increasing if you are increasing the problem size, if you are increasing W, how judicious is it to increase P? Now, the next question which comes to us is that even after doing all these things, what is the best efficiency that we can get? And for that we use Amdahl's law, that everything we consider that there are certain overheads which will reduce the efficiency, and efficiency will increase if we have larger problem, efficiency will reduce if we increase number of processors, fine. Now, what is the best possible efficiency? So that we try to achieve that efficiency. So now if we look into a parallel algorithm, we understand that the entire algorithm is not parallelizable. Some components such as joining results from threads, like when we are calculating maximum out of n numbers in P processors, each local n by P max values will be joined, or writing or reading from a file, some IOs, they are inherently sequential, that joining the thread results or reading from a file. There are certain components doing the load balancing, deciding how many data points will go to which processors. All these things, they are inherently sequential, they cannot be done in parallel. Either one computer will do it and let others know, or all the computers have to repeat the same step. So there are always some sequential part in an algorithm which we cannot parallelize. So Amdahl's law gives us a quick method to estimate the speed up in that case. Let a serial program of data size n runs in Ts time, which has two components. One is phi s n, which is not parallelizable. The total time is Ts for a sequential program, and it has two components. One part is not parallelizable, essentially sequential, which is phi s, and another part is parallelizable, which we write psi n. So when we parallelize it, we cannot do anything with phi s. This is sequential time. In any parallel algorithm, this time will be present. But this psi, it can be distributed in many processors, and we can reduce this time. So the total time for this sequential program is phi s plus psi n, and the parallel execution time Tp will be sum of the serial non-parallelizable part phi s, it will be always there, it cannot be parallelized, and then the parallelized part can be divided by P if we are using P processors. So, and there is a overhead. So the sequential the parallel time will be phi s P, which is present, psi n divided by P, because this is the parallel part of the algorithm which can be reduced by using multiple computers, and psi n by P, plus an overhead which we have discussed earlier, an overhead T0 n by P. So speed up is Ts by Tp, and this is psi s plus psi n divided by phi s plus psi n by P plus T0 n by P. Now we assume that the sequential part of the program, the time requirement for that is f for the entire program time. The total time of the run of the sequential run is psi s plus phi s plus psi n, and the sequential time is phi s, and f is the ratio of the fraction of the program of the serial algorithm which cannot be parallelized, the ratio of the sequential time divided by total time, which will help us to parameterize the previous expression. So, so the speed up bound we can obtain as the speed up is equal to phi s, we got this formula, plus psi n plus phi s plus psi n by P plus T0 by n by P, and as T0 is always greater than 0, overage is always greater than 0, speed up is bounded as s is less than phi s plus psi n divided by phi s plus psi n by P. Now we know that phi s plus psi n is equal to phi s by f. So we substitute all the terms and we get speed up is less than phi s by f plus divided by phi s plus phi s into 1 by f minus 1 by P, whole by p, and phi s phi cancels out from both the sides, and we get speed up is less than 1 by f plus 1 minus f by p. So, if f is the sequential fraction of the program with p numbers of processors, this is the maximum speed up that we can get. Due to overheads, speed up is less than equal to that. We cannot think of getting higher speed up. And our attempts can be only made to get speed up as close to this particular value. And this is known as Amdahl's law, which gives us maximum theoretical speed up for a parallel program. A fraction of the program, it understands that a fraction of the program is inherently sequential and it always holds up the scalability. So, we got that speed up is less than 1 by f plus 1 minus f by p, is less than equal to that. It is usually less than that because overhead is always positive. And so, this is bounded due to overhead. And the limited cases are, one is that the algorithm is mostly sequential. Say we are computing Fibonacci series, we cannot parallelize it. Even if we are using multiple computers, all have to do same things, or every computer has to sit idle except one computer which will process it. So, if or the sequential part is very close to 1, and if is equal to 1, this term will be 0. So, speed up will be less than 1 because there is an overhead, so speed up is less than 1. So, it is a sequential program, but if we run it in parallel environment, speed up will be less than 1. As many processors as we are using will not see any benefit, speed up is always smaller than 1. Why it is not 1, why it is less than 1? Because there are overheads. If we are using parallel environment, multiple computer processors are there, they are interacting in between them, and that is adding to overhead. So, that is the most unbeneficial part. In case the speed up is less than 1 means parallel platform of strictly sequential parallel performance of strictly sequential algorithm program is always poor than single processor performance due to parallel overheads. In case the algorithm has negligible sequential component, almost the entire program can be parallelized, f goes to 0, we get speed up is less than p, s is less than p. So, speed up is less than p is not exactly p due to parallel overheads, and in between we will get a value of speed up which is 1 by f plus 1 minus f by p. So, if we know the algorithm, if we can do an analysis and find out how much sequential steps are there and how many parallelizable steps are there, we can find out what is the maximum maximum bound on its parallel speed up, and that is what we can try to achieve, and this is what is specified as given as Amdahl's law. It is a very important law in parallel programming. So, these are the references we got here, and through this discussion we noted down the matrix for performance of parallel system, saw the relation of efficiency with the problem size and number of processors, and looked into isoefficiency functions, and Amdahl's law is discussed, which gives us the theoretical maximum speed up for any algorithm. And with this we can look into our we can start discussing on parallel programs, and we'll start discussing on OpenMP next, then MPI followed by CUDA discussion, and whenever we'll try to parallelize a program and try to see its performance, we have the fundamentals in our mind, and we can estimate how good is our parallel algorithm compared to the best theoretical parallelization possible of that problem. Thank you.